right, so it's time to do an example and put all of these crazy ideas into play. Now again, this is an integral that we would not have a direct technique to apply. So this is going to give us an idea of how good our estimates are. Unless you want to do these by hand, which I don't think you would want to, you're going to go to the Riemann sum calculator that we've worked with. You would put in your formula. Now, when you type in sine of x squared, you have to do it in the Mathematica way, meaning sine has to be capitalized, you need a square bracket, you need to put your x, caret 2, close square bracket. We are doing the integral from 0 to 1. We want 10 rectangles, and I want to get the midpoint estimate. So you can see here, I've got an estimate. I'm going to take 5 decimal places of it. That's what your book opts to do. I can get my left and right approximation the same way, and then I can find the trapezoid simply by taking the average of the left and the right. As you can see, I've written down the estimates, and again, I got the trapezoid by averaging left and right. And the next thing that you need to do is these error-bound theorems all talk about what's happening with the first derivative, what's happening with the second derivative. So I'm going to go here and I'm going to say what my original function is by reading it from the integral. It's sine of x squared. You need to calculate the first derivative of that. And keep in mind this would be chain rule because inside the parentheses you don't just have a plain x, you have an x squared, a function of x. So the derivative of sine, you start by taking derivative of the outside function, is cosine, leave the inside function the same, times the derivative of the inside function, which would be 2x. Now again, to avoid confusion here with this angle and this multiplier, we usually put that multiplier out in front. So that's my first derivative. And my second derivative, I need to take the derivative of this. Now, in order to do that, you need to use something called the product rule. And the product rule works by splitting your function into a product of two functions. So I'm going to do that with color. Okay, so I'm choosing to split it the multiplication between the 2x and the cosine x squared. Product rule says you take the first function, leave it the same, times the derivative of the second function. Now to take the derivative of this function, keep in mind that's chain rule again. So with my color coding, this is keeping the first function the same, taking the derivative of the second function, and then adding to that, we take the derivative of the first function, derivative of 2x is 2, times the second function stays the same. So again, with my colors, this is the second function staying the same. The 2 came from taking the derivative. So again, it doesn't matter what order you do these in, but in one term, you leave the function the same. In the other term, you take its derivative and you switch it up between first and last. So the simplified version of the second derivative is going to be 2x times 2x is 4x, and I've got the negative that's here. So negative 4x sine of x squared plus 2 cosine x squared. Oh, and I forgot, 2x times 2x is not just 4x, it's 4x squared. Sorry, my bad. All right, so that's our second derivative. Now, in order to find k, these constants that we have to choose, we want to look at the graphs of the first derivative and the second derivative. And ideally, not only do we want to look at those graphs, but we need to consider their absolute value. Okay, again, we don't care about the signs. All right, so you should have the ability to graph using a graphing calculator. I'm going to use the website desmos.com, which is again a nice free graphing application. All right, so I've gone to Desmos and I've put in my function, which is 2x times cosine of x squared. This is the first derivative, remember? And this is quite the funky graph, but remember, we don't have to care about all of this. We're looking to approximate the integral that goes from 0 to 1. So I can tell Desmos to get rid of all the noise, bounding x between 0 and 1. Remember, this curve represents the derivative. So each point on here is reporting a steepness at an x value. So as I climb up, you can see that my steepness takes on the largest value right here, and at x equals 0.808, and the steepness that it takes on is 1.284. So your book says, a decent estimate for K1 would be 1.5. I'm going to take exactly 1.284 and do the calculations with that, just to show you what the difference is when you use an upper bound that's above the highest or most steep point versus using the bound to be that exact highest steepness. So K1 appears in the error-bound formula for the left and the right sums. So that's what I'm going to calculate first. So the formula says that we can find the area between the exact value of the integral and my left approximation, and that it will stay less than K1 times b minus a squared over 2n. So I'm going to go ahead and substitute the values on the right. So I'm switching to an equal sign because this formula is going to be equal to what I put next, 1.284. B and A are upper and lower limits, so 1 minus 0 squared over 2n is 2 times the number of subintervals, and the number of subintervals, again, for all of these approximations was 10. So you're going to want to crunch that down to a single number. And I got that to be 0.0642. So I know that the error produced by the left approximating sum is going to be at most 0.0642. And your book discusses that most often that's the worst case scenario. Your error is usually less. So they call this being pessimistic. So the worst error you're going to encounter with the left approximation is this. Now, because the error formula for left and right are identical, that means I also know that the worst error that's going to occur with the right approximation is going to be that much. Just for comparison's sake, your book took K1 to be 1.5. And when they go through and do their calculations, they ended up having an error bound of 0.075. So you can see that our error is lessened when we choose a constant as close as we can to the maximum steepness that occurs on the graph. All right, now in order to choose K2, I need to be looking at the graph of the second derivative for this function. So back to Desmos we go. So here's the graph of the second derivative, which again has a whole lot of noise going on, bounding x between 0 and 1. Okay, so remember, this is a second derivative, so this is telling us about concavities. So if we trace along the curve here, by tracing along here, I can see that the maximum value that the concavity is going to take on is a value of 2, and it occurs at a couple of different x values. But you need to consider the other end of the function as well. My largest function value, in terms of its absolute value, is here at this end. It's 2.285. Just to make sure that I've got the right value for k, you can just do algebraic calculations and say, okay, well, I want to look at what's happening at the left end of the interval that we're integrating over, because it seemed like that had a particular value. And then I want to look at the other end when it reaches 1. So you can go through and you can substitute both of those quantities into this statement up here. And when you do that, you're going to get 2 for this value. And at 1, when you substitute ones all the way across, you have, I do get that this is negative 2.285. as Desmos showed us. So if you are having trouble tracking down those values on your graphing calculator, that's, a quick way to get them just by plugging in. And again, we're considering the absolute value of these, and when you take the absolute value, the second one is the larger value. Remember, we use the y value because we're looking for an upper bound. So we're going to take 2.285 to be our k. Now again, your book uses a slightly different one. We'll see the effect. Remember, there's different formulas for midpoint and for trapezoid. So we are going to have to do 2 calculations with this k value. Substitute all the numbers. And the error I get in this case is 0.0019. When your textbook did this, they used a value of 3. And the corresponding error bound that they got was 0.0025. Choosing a tighter constant to the function reduces my error bounds, so guarantees a more accurate prediction. And now we do the midpoint calculation, just being careful to switch to the midpoint formula. So again, substitute and calculate. And this time I get 0.0000. Now it's a 9.5, so I guess technically I should round that to be a 1.0. Okay. Of all of these, you have the least possible error occurring with the midpoint approximation, and it's only going to be off by a maximum of 1/1000th, which is a pretty good approximation considering you can't get the exact value by algebraic means. The error bound theorem will give you some degree of confidence in terms of how close your estimate is to the actual value of the integral. But the more powerful version of this is putting us in control of that error. So I can use the error bound theorem to tell me how many subintervals to use to achieve a certain specified accuracy. So realistically, if you're doing calculus in the real world, very often in engineering fields, that kind of thing, you would have some idea of how accurate you need an integral to be.